So, before anything else, the two voices explaining AI to you, well, they are themselves AI.
Yeah, which is, either poetic or ironic. We have not decided.
Right. The research and the writing are dance. The voices are us.
Exactly. Machine voices, human mind.
Welcome to Plain Strata, where we take decentralized AI apart one layer at a time. This is the layer, one idea taken all the way down, and today it is about proving an AI answer was computed correctly using mathematics instead of money.
Right, because, imagine putting a supercomputer on the witness stand, forcing it to mathematically swear it did not cheat on a single calculation, and then just walking away with an ironclad cryptographic guarantee.
Yeah, which sounds crazy, but this summer, a company named Lagrange produced the first actual cryptographic proof that a language model ran. The model they used was GPT-2 from 2019, which is small enough to sit on a phone at about 124 million numbers.
And the really fascinating part is that the hardest thing to prove in it was not the huge matrix multiplications. It was actually softmax, which is the step that turns scores into probabilities.
Wait, really? Just the probability part?
Yeah, and that specific hurdle tells us everything about what we are exploring today. Cryptographic proof is the only check on an AI answer with no deposit and nobody to trust. And its price is that a model must be made countable before it can be made accountable.
Countable before it can be made accountable.
Yeah.
Okay, I like that.
That trade-off is the absolute core reality of this space, and we are going to return to it constantly.
Well, proving a massive computation ran cryptographically without trusting a single human or machine involved feels like pure magic. But magic does not really help you understand the mechanics.
Oh, it does not?
Before we get into the math of a proof,
yeah,
we need to physically picture what the AI is actually doing when you type in a prompt.
Right, so we have to separate the actual model from the proof system watching it. When you ask a language model a question, your text is chopped into smaller pieces called tokens. Each token becomes a number, and that number looks up a row in a massive table, which then spits out a new list of numbers.
Okay, so just a giant lookup process to start.
Exactly. And then that list flows through a stack of identical blocks. GPT-2 has 12 of those blocks. Inside each block, your numbers are multiplied by weight matrices, recombined, and then added back onto themselves. Finally, one last multiplication produces a score for every single word the model knows, and the word with the highest score wins.
And that entire journey through the 12 blocks, that is just one forward pass. It happens in, milliseconds on a server somewhere. The model grabs that winning word, sticks it onto the end of your original prompt, and then runs the entire gauntlet again.
Right, which means a 100-word answer requires 100 forward passes. Now, picture the proof system sitting alongside that model. A totally separate mechanism runs the exact same computation, but it records everything.
Like every single step.
Every single step. It records every intermediate value, every product, and every single number that ever appeared on any wire inside those 12 blocks. Then it takes that massive historical record, performs a huge amount of mathematical work on it, and squeezes it down into a tiny file.
Oh, wow. So proving the math takes vastly longer than just doing the math in the first place. The original generation takes milliseconds, but generating the proof, that has to cost a small fortune and take serious computing power.
Yeah, but that asymmetry is the whole point. Proving is expensive and happens once in a private room. Verifying that proof takes milliseconds and can happen millions of times in public.
Huh, okay.
Think of a master chef cooking a highly complex dish behind a closed door. You need to know that a proprietary recipe was followed exactly. But you are not allowed to see the recipe, and you cannot look at the raw ingredients.
Right, because if I just ask for a photograph of the finished plate, that does nothing for me, since a bad chef can easily plate a terrible dish to look perfect.
Exactly.
And if they just send me a video recording of the cooking process, well, that reveals way too much. It exposes the secret recipe to the public. Plus, nobody has the time to sit and watch a video of every single meal being cooked anyway.
Right.
Wait, if you just use a standard server log file, why would that not work?
Because a dishonest operator can just type up a fake log file that looks pristine. What you actually need from that chef is a small slip of paper. If the chef deviated by a single gram of salt at any point in the cooking process, the math on that slip of paper changes completely. You can spot the lie instantly. That slip is the zero-knowledge proof.
That makes sense. Wait, let's define those terms for the listener really quick. Where do these words actually originate?
Oh, sure. The word prove comes from the Latin probare, P-R-O-B-A-R-E. It means to test, to try, or to find good without an audience.
Oh, without an audience.
Yeah, we usually think of proving something as a public demonstration, but the original route is about testing something in isolation to see if it survives the stress. And the term zero knowledge, that is a strict mathematical promise about what the checker walks away with. The verifier ends up knowing exactly what they knew before the test, nothing more.
So they learned this statement is true, but they learned zero details about the hidden ingredients. Okay, so we have our chef behind a closed door, and we need this magical slip of paper. But forcing an AI to generate that paper took years of engineering because the math systems are completely incompatible, right?
Yes, very incompatible. The notary stamping our proof only understands addition and multiplication in what is called a finite field. A finite field is a set of whole numbers from 0 up to some large prime number.
Okay.
The arithmetic wraps around when it hits the top limit, very much like a clock face. If it is 10 o'clock and you add 3 hours, you do not get 13 o'clock, you get 1 o'clock.
Huh. But neural networks absolutely do not operate on a clock face. They live in floating point arithmetic. Those are, approximate unevenly spaced numbers with endless decimal points that just round off at every step. Yeah. You cannot put a floating point number like 0.7231 into a clock face math system and expect the notary to stamp it.
Right, which forces the very first move, quantization. The root of that word is quantus, meaning how much. It basically means chopping a smooth, infinite continuum into countable, discrete steps. Before you can apply any cryptography, you must convert the entire floating point model into integers.
Which goes right back to the rule you mentioned. You have to make a model countable before you can make it accountable.
Exactly. To use the kitchen analogy, you are forcing the chef to only measure ingredients in whole grams, no fractions allowed.
So Lagrange ran GPT-2 at 12-bit quantization, which means every single weight and every intermediate value was brutally rounded to become one of 4,096 possible integers.
Right.
And when they did that, they achieved a 99.6% cosine similarity. Wait, hold on. For those tracking the math, that cosine similarity basically means the answers are 99.6% identical to what the unquantized model would say.
Yeah.
But that missing 0.4%, that is where the danger actually lies, right?
We will definitely explore that missing fraction. But once the model is converted to integers, you hit a much stranger problem.
Wait, if the model is just whole numbers now, matrix multiplication is just a massive pile of adding and multiplying. And our clock face notary speaks addition and multiplication perfectly. So that part should fit the finite field without any resistance, right? The whole model is easy from there.
Well, the matrix multiplications are completely fine. If a language model was only matrix multiplication, this entire field would have been solved years ago.
Oh, wait.
But most of a transformer relies on complex functions. You have softmax, which exponentiates each score to turn them into probabilities. You have GLU, which is the activation function inside every single block. You have layer norm, which requires calculating a square root.
And exponentials and square roots simply do not exist in a finite field. A clock face cannot calculate a curve.
Exactly.
So how do you prove an operation that your own proof system cannot even mathematically express?
The workaround changes the entire nature of the proof. They use lookup tables. Because the inputs are strictly limited to 4,096 possible values due to that quantization step, the engineers pre-compute all 4,096 answers in advance.
Oh, wow. They just store those answers as a permanent list.
Yes. Proving that softmax was applied correctly stops being a claim about computing an exponential function. It becomes a claim about membership. The prover just has to show that the input and the output match a specific row in that pre-computed list.
So the chef is no longer cooking the sauce from scratch. They're using a pre-approved menu of combinations. And the proof just checks that they picked an item that actually exists on the menu.
Precisely. The hard computation is moved out of the cryptographic proof entirely.
Okay, that solves the individual operations in isolation.
Yeah.
But the physical layout of the model immediately creates another barrier.
Yes, and we need to define the word circuit here. In cryptography, a circuit is a fixed arrangement of gates and wires. There are no loops, and there are no conditional if statements. Every single gate fires exactly once in a strictly fixed order. The problem is that transformers are not simple stacks of layers. They're complex graphs.
Right, because they have residual connections. The output of an attention step is added back onto the original input that went into it. That kind of creates a branch and a merge in the wiring, which completely shatters the simple top-to-bottom circuit model. They had to build support for arbitrary computation graphs just to read the model files correctly.
Exactly.
But I'm still hung up on something. Why is softmax considered the absolute hardest part of the AI to prove if they just replaced it with a simple lookup table?
The difficulty stems from the severe danger of precision loss. Exponentials have a massive dynamic range. A tiny microscopic change in the input creates a catastrophic change in the output. When you force that sensitive curve into fixed point integers, the approximation error compounds rapidly.
Oh, I see.
And this is not just a problem of accuracy where the answer drifts a little bit and the essay sounds slightly worse. It is a problem of soundness.
Soundness, meaning preventing a liar from slipping through the cracks. If there is slack in the mathematical approximation, a dishonest operator will exploit that exact slack to forge a valid-looking proof for an output the model never actually produced.
You hit the nail on the head. Accuracy is a negotiable quality metric. Soundness is a strict binary. If you lose soundness, the entire proof system is worthless. Which brings us to the sheer scale of the computation. Because, a model does not run one time.
Right. As we established, producing a 100-word answer means 100 forward passes. The proof cannot be a static, frozen object. It has to be an ongoing chain that carries state across steps, mirroring how the AI carries its own memory forward.
Yes, and if we took that chain of 100 forward passes and flattened it into a single giant mathematical system, the file size would be astronomical.
You would spend 3 days just trying to download the proof file, like on a hospital guest network.
Proving cost scales linearly with the number of constraints, and for a long time, the cryptographic field just kept hitting that physical limit. To avoid generating a file the size of a planet, we need to look at the mechanism operating underneath all of this.
We probably need a physical analogy here before we lose the listener in the cryptography.
Yeah.
Let's talk about folding.
Okay, the mechanism relies on refusing to check everything directly. This is built on a mathematical protocol from 1990 called SumCheck, and a 2008 protocol named after its creators, Goldwasser, Colley, and Rothblum. The verifier makes the prover take an enormous sum of calculations and fold it into a small, single-variable expression.
So imagine a massive sheet of paper covered in millions of equations. Instead of reading every line, you force the prover to fold that sheet intricately, over and over, until it is a tiny square. Then the verifier takes a sharp pin and pokes it straight through the folded square. That pinprick is the random challenge. If the prover lied anywhere on that massive sheet, the layers will not align properly. When you unfold the paper, the pinholes will not follow the expected mathematical path, and the lie is instantly exposed.
The beauty of the pinprick is that it wraps around the layered computation of the AI model. They reduce a massive claim about the output of the final layer to a slightly smaller claim about the output of the layer before it. Then they do it again to the layer before that.
Oh, they walk backward?
Yes, layer by layer, all the way to the initial prompt. The prover never commits to checking every single wire in the machine simultaneously. It commits to the boundaries and lets the interrogation walk backwards through the middle.
The pattern you were describing is vital.
Yeah.
You narrow the claim, you do not check it. It is very much like a binary search. Think of two rival corporations trying to settle a massive financial dispute. Instead of hiring accountants to audit every single transaction from the beginning of the decade, they just have the disagreement.
Yeah.
Then they have it again. They keep having it until the massive dispute collapses down to one single, easily verifiable receipt that anybody can look at.
And this structural reality connects right back to our original point and why softmax was the hardest obstacle. This entire challenge and response game sits deep inside cryptography, running in private in microseconds. The expensive thing in this world is not doing a vast amount of arithmetic. The expensive thing is any step that cannot be folded and interrogated cheaply.
And softmax heavily resists that folding process.
Exactly.
So we have covered how the claim is narrowed through folding and how the lookup tables handle the math. But we really need to look at the permanent cost of this entire process. Let us go back to our golden rule: countable before accountable.
Quantization is the strict, non-negotiable entry fee. When Lagrange reports a 99.6% similarity to the original floating point model, that number is merely a measurement of quality. It is absolutely not a cryptographic proof.
Right.
That remaining fraction of a percent of divergence, the slight weirdness introduced by rounding the numbers, that sits completely outside the protective wall of the proof.
This is a crucial foundational distinction for anyone listening. A proof of the quantized model is not a proof of the original model. Cryptography certifies fidelity to a rigid specification. It never certifies fidelity to an intention.
Right.
The proof guarantees the computation ran exactly as the integers demanded. It does not prove the computation was safe or unbiased, or that it was even the right model to use for the job in the first place.
We can ground this limitation in a real-world application. A major hospital wants to run a diagnostic language model to analyze patient histories. The stakes for getting the math right are incredibly high.
Right, because the hospital has highly protected health data that legally cannot leave the premises or be leaked. And the company providing the AI has proprietary weights that cost millions to train. And they definitely refuse to hand them over to the hospital's IT department.
So the original AI model is converted to 12-bit integers once offline. That is where the seam opens between the original model and the countable model, and it never closes. The prover mathematically commits to those integer weights, sealing them in a cryptographic envelope.
Then the patient's medical text is tokenized into numbers. Each token looks up a row in the embedding table, which is proven to the notary as simple membership in a list, like we talked about.
Yes. Then the numbers flow into the 12 blocks. The massive matrix multiplications are handled natively by the clock face math. Softmax is handled through bounded tables to prevent any precision slack from letting a liar slip through.
The residual additions branch and merge the data. The final multiplication scores the medical terms. One diagnostic word is omitted, appended to the patient file, and the whole sequence runs again.
Proofs are omitted step by step, walking backwards, folding the claims like that origami paper. Eventually, the medical regulator receives a very small file. They run a verifier program on it in a few milliseconds.
And the regulator learns absolutely nothing about the patient's private medical history, and they learn nothing about the company's proprietary AI weights. They only learn that the stated quantized model produced the exact output sitting on the desk.
The proof is exactly as wide as the mathematical specification and not 1 millimeter wider, which leaves us with the immediate market reality of this technology. If zero-knowledge AI works, but is strictly limited to integers and exact specifications, who actually needs to buy it right now?
Right, that is the big question.
There are two massive open questions defining the space. The first is purely technical. Does this proof chain compose recursively? If you prove a 100-word response, you generate roughly 100 proofs. If you cannot mathematically fold those separate proofs into one single master proof, this technology remains structurally poor for generating long, complex AI answers.
Yeah, that would be a huge bottleneck. And the second question dictating the market is about the global regulatory timeline. In the summer of 2026, the European Union deferred their high-risk AI obligations to December 2027. They gave companies breathing room.
They did.
But the transparency and marking obligations, the rigid rules saying you must loudly disclose when a machine generates a piece of content, those stayed firmly on schedule.
And that aggressive split in the legislative timeline is critical for adoption. Provenance, creating a digital receipt that simply answers whether a machine made a piece of content, is incredibly cheap. It requires a standard digital signature, not a heavy cryptographic proof system. Correctness proofs, which prove the internal math of the neural network was done perfectly without tampering, those remain highly expensive.
So simple provenance might eat the commercial market first because basic receipts are cheap and they satisfy the immediate transparency laws. But correctness proofs are finding a very different home. Defense procurement and high-stakes decentralized finance are buying these proofs right now.
Yeah, they are not waiting around.
They are not waiting for a compliance deadline or a European regulator to tell them what to do. They are buying correctness proofs because they genuinely cannot trust the operator running the model on the other side of the world.
A technology depending on a legislative calendar is always fragile. A technology depending on the absolute reality of zero trust is not. That was the why, the how is the rest of the show, and no background is needed. If you can follow a story, you can follow this.
This is plain Strata. Decentralized AI, layer by layer.